Okay, cool. Now I share my screen. Sorry if there's like a background noise. Someone's doing renovations upstairs. Okay, so yeah, before we start with this week's stuff, I just want to go back to this question from last week because I made a mistake with this. So I can't remember. I think it might be, was it Rowan that asked the question like, how come we're doing this? We eventually got like a expression for d cos theta, the energy, and then we minimized that, and then from there we said, okay, we found the extrema for the cos theta. So actually, if you're doing that, he's correct. That's not finding the maximum angle because as cos theta get larger, the angle gets smaller. So this is actually the minimum opening angle. So if you're doing the question that way, you're basically saying find the minimum opening angle and find the energy relation that gives give that angle to. So what we did last week when we found, I think theta was it 0.2 or something? Yeah, I think it's 0.027. So that's the minimum angle. So if you're going to do this question to find the maximum opening angle, then the question is kind of pointless. You have to rephrase it, because if you find a maximum angle, then you can just say that the maximum opening angle is just pi. Is equal to pi. And then now that you know the maximum angle there, you can put this back to find what photon energy corresponds to this max angle. So you're kind of doing the question backwards if you're talking about a maximum angle, because that's not determined by the energy. That's just, you can just physically argue it. So yeah, if you're going to do it the way that we did last week, then yeah, the answer is actually finding the minimum angle. So yeah, sorry about that. Okay, any questions about that one? Like, hopefully it's clear by now. Okay, if that's all good, then let's look at this week's stuff. So we're definitely not going to be able to get through everything this week. So if you have any particular question that you want me to specifically go through, please like speak up now or put it in chat. So I'll prioritize those ones. Otherwise, I'm just going to randomly pick a couple, like one from each of the 3 topics, and then go through those. Maybe it'll help if I share the questions and then you can have a look first. Yeah, so any preferences for any of these 3 topics or any questions in particular? No one? Everyone's just happy to go through whatever? Okay, then all good. Then we will just go back to the OneNote. Okay, okay, since we're on this page, then let's just start with this. Okay, so SU2 and the polysigma matrices. So SU2 is a group. So it's a group specifically, usually like most often represented as 2x2 matrices, but could have other representations. But the defining feature is this unitarity and also the determinant being 1. If the determinant is not 1, then you just cross out the S. It's not that special. It's just a unitary group. Okay, so for question 1, show that you can construct a unitary matrix out of any Hermitian matrix H using this matrix exponential map, and that the special unitary matrix satisfies, in addition, that the trace of this Hermitian matrix must be 0. Okay, so to do that, let's just write out U equals e to the IH. And we just gotta look for this relationship. So U bar U has to equal 1. And U bar in this case, if given this kind of representation, is just going to be e to the minus IH conjugate, Hermitian conjugate. So then U bar U is going to equal to e to the IH minus H dagger. And since H is Hermitian, then H dagger is equal to H. So this is equal to e to the 0. So that is equal to 1. So perfect, that checks out. And then if you look at the determinant of U, And in this case will be determinant of e to the IH. And you're gonna have to trust me on this. This is equal to e to the I trace of H. So this is called the Jacobi formula, depending on what language you speak. And so yeah, like determinant of like exponential maps into the exponential of the trace of that matrix in the exponent. And since this has to be equal to 1 because it's a special unitary matrix, so that just tells me the exponent has to equal to 0, can't be I, so that means trace of H must be 0. So yeah, that's the second statement. Okay, number 2, show that a special unitary matrix, 2x2 matrix, has 3 real degrees of freedom. Okay, so if you look at a special unitary matrix, it's a 2x2 matrix, but each one is a complex entry. So it's a 2x2 complex matrix. So that tells me it has 4 complex numbers. And agnostic to what the matrix entries has to be, if they're just allowed to be whatever it is, then that's 4 complex numbers. Complex numbers each have 2 degrees of freedom each, the real and that imaginary part. So in a 4x4 matrix, that in total gives us 8 degrees of freedom just for a 2x2 complex matrix. But now we are requiring for the special for the unitary condition, so u bar u has to equal to 1. So if we call this matrix some the entry some random stuff like say alpha, beta, gamma, delta. So if that's u, okay, and then that tells me that u bar u equal to 1, which is in other words like a 2x2 identity matrix. So then that will be alpha conjugate, gamma conjugate, beta conjugate, delta conjugate times by alpha, beta, gamma, delta. So then that equals alpha bar alpha plus, what, not beta, sorry, gamma bar gamma, alpha beta bar plus gamma delta bar, alpha bar beta plus gamma bar delta, beta bar beta plus delta bar delta. Okay, cool. And this has to equal a identity matrix. So this has to equal 1, 0, 0, 1. So then that just tells me I have 4 equations. I have to make sure that alpha bar alpha plus gamma bar gamma equals 1. This has to equal 0. This has to equal 0. And this has to equal 1. So that's 4 equations. 4 equations that essentially fixes what alpha, beta, gamma, delta, how they relate to each other. So since I got 4 equations, that's 4 constraints. So I lose 4 degrees of freedom here. And then the final one is demanding that a determinant of u is equal to 1. So that loses me another degree of freedom because it's another constraint on what the parameters are allowed to be. So then 8 degrees of freedom start off with a general 2x2 complex matrix. The unitarity and the determinant subtracts 5 degrees of freedom. So altogether, I have 3 degrees of freedom remaining. And so the SU2 matrices have 3 degrees of freedom. Okay, and the question 3 is very closely related to that. So it's asking how many independent parameters have a traceless Hermitian 2x2 matrix. English is not that great here. How many free parameters are there in a traceless 2x2 Hermitian matrix? So we asked this because in question 1, we showed that you can express a unitary matrix in terms of a exponential of a Hermitian matrix. So you'd expect that you shouldn't get anything different. You should also get 3 degrees of freedom because otherwise, depending on which way you represent the matrix, you're going to end up with more degrees of freedom. That doesn't make a lot of sense. But let's try that anyway. So for part 3, so now we're looking at a 2x2 Hermitian matrix, which again is a complex matrix. So each entry is allowed to be a complex number. So we again start off with 8 degrees of freedom. But now the requirements are a bit different. So for Hermitian matrices, we know that the Hermitian conjugate has to equal to itself. So when you conjugate something, you flip the off diagonal components and then you conjugate them. So the diagonal components don't get flipped because in the transpose operation, so okay, if you don't know, the dagger means you transpose and then complex conjugate the whole thing. So when you transpose the whole thing, the diagonal components don't get moved. And if you require the complex conjugate to be the same as the itself, then that means the diagonal components must be real. So that minus 2 degrees of freedom because I have 2 diagonal components. And then because 2 by 2 matrix, that means you have 2 off diagonal components, and they have to be kind of, when you flip them and complex conjugate them, they have to be the same. So the off diagonal components, so one of the off diagonal components fixes the other one. It demands the other one has to be the complex conjugate of that. So one off diagonal component fixes the other. So we lose another complex number because one of the components is fixed. So that's minus another 2 degrees of freedom. And finally, we're demanding it to be traceless. So trace of H is equal to 0. So that's minus another 1 degrees of freedom. So altogether, again, 8 minus 5, we end up with 3 remaining degrees of freedom. Okay, all good? All right, then, okay, might as well just do question 4, then it's pretty straightforward. Show that a special unitary 2 by 2 matrix can be written in terms of the Pauli matrices. Okay, so this has a fairly short answer and a fairly long answer. So the short answer is just that if you look at the Pauli matrices, sigma I, so 3 of them, they are traceless and Hermitian. So you can go back to question 1 and say, okay, if there's a traceless Hermitian matrix, then you can write any unitary matrix as an exponential of I to the theta I. And that satisfies the requirement that we show that any Hermitian matrix can be used this way to generate a unitary matrix. So if the Pauli matrices satisfy tracelessness and the Hermitian nature of it, then they must also fit. Slightly longer answer is that if you look at the structure of the 3 Pauli matrices, so if you look at a commutator, so sigma I, sigma J, sigma K, if you commutate them, then that gives you 2I epsilon JKL sigma L. So if you rescale them, so the set of I times sigma K, so the 3 Pauli matrices, but then multiplied by I, and sometimes you'll see a half in there as well, just for like a normalization issue, not really physically important. But these 3 objects, they satisfy the commutation relation that makes them a real 3-dimensional algebra. And this real 3-dimensional algebra is isomorphic to SU2, which is the, okay, imagine this to be the math frac SU2. So it's this 3-dimensional algebra generated by spanned by the Pauli matrices. It's the same as the one that is used to generate SU2 group. So this is the generator for the special unitary group of order 2. So you can think of these fundamentally as the 3 Pauli matrices form like a basis vector for the SU2 group. So you can use them as basis vectors, and a linear combination of them can then generate you all the elements inside the SU2 group. So it's just a kind of a fancy abstract algebra way of writing basis vectors. I'm not sure how much Mikhail actually wants you to know this. I'm pretty sure if this shows up in the exam somehow, this sentence is sufficient to get you the mark. This is kind of like maybe he'll be. To be honest, I don't really know how deep he wants to get into this. Okay, any questions? Okay, if not, then let's go do another question some other place. Okay, let's do a Dirac equation question. So starting from the Dirac equation in the momentum space, so this is the Dirac equation, derive the corresponding equation for the adjoint spinor, so the U bar. Also, without using the explicit form of the spinors, show that the normalization condition U bar U, U dagger U, sorry, is equal to 2 times energy, and it leads to these two relations. Okay, let's do the first part first. So let's just derive the corresponding equation. So if we start off with the Dirac equation, U of P is equal to 0, and then we multiply it by the gamma naught. So we take this equation and then we dagger it, and then we multiply it by gamma naught on the right. So then we end up getting P dash minus M U of P daggered and then gamma naught, and that's equal to 0. Okay, if you transpose conjugate this entire thing, so the everything in the bracket, notationally that means you flip the order of everything. So U is the last one in this equation, but then once you dagger the whole thing, U becomes the first thing. So kind of think of it as like a conjugation, transpose, like a matrices where you swap the off diagonals, but when you write in the equation, you swap the order of the things. So you start off with the U dagger P, and then you get everything inside. So then you got first, let's write out the slash notation in explicitly. So you got gamma mu dagger and then P mu. P is the momentum operator. So momentum operators, if you remember from quantum mechanics, are Hermitian. So daggering them doesn't do anything. So I can just save the dagger in this case. M is just a number, also doesn't get conjugated because it's a real value. And then we'll end up with the gamma naught. That equals 0.
Sorry, can you please repeat again why you daggered the expression and times it by gamma naught?
Just because this is how you derive the adjoint equation. Yeah, there's no real physical motivation for why I'm doing this. Oh, there probably is, but it's beyond me. It's probably when Dirac was first writing down these equations, probably has some reasoning for it. But yeah, that's just what we do. Okay, so yeah, now that we have this, then we use the identity from the gamma matrices. So gamma mu daggered is by definition gamma naught, gamma nu, gamma naught from the Clifford algebra. So we just sub that into here. So we get U dagger, gamma naught, gamma mu, gamma naught. And then we now take this gamma naught into the bracket, and we can just put it in here and P mu. We can put it in front of the P because if you think about the momentum operator operates on the momentum part of the Hilbert space, and the gamma matrices are the spin part of the Hilbert space. So they're technically two completely separate subsets of the Hilbert space. So they don't interact with each other. So you don't have to worry about commutation relations. You can actually just swap the order of them without having any issues. So I can put this, when I multiply it into the bracket, I can put it in front of the P without any issues. And since M is just a number, it also doesn't care. Okay, and now we use the relation that gamma naught times gamma naught is just equal to the identity matrix. So it's just equal to 1. So this gamma naught cancel each other out. So we get U dagger P, gamma naught, gamma mu, P mu, minus M, gamma naught. Okay, now that we just take another factor of gamma mu out, gamma naught out, but to the left. So U dagger P, gamma naught, and then gamma mu, P mu, we can reduce this with a slash notation again, minus M, and this is still equal to 0. And remember the adjoint operator's definition is the Hermitian conjugate times by gamma naught. So this is now the adjoint operator. So we get U bar P slash minus M is equal to 0. So that's the Dirac equation for the adjoint spinor. Cool. Any questions for this? Okay, if not, then let's move on to getting these two out. So, okay, to move this out of the way so I can have a bit more room. Okay, now that I have the adjoint Dirac equation and the normal Dirac equation, I'm going to take the normal Dirac equation and then multiply it with a, so I can take the P minus M U, and I multiply with U bar gamma mu on the left. And because it's equal to 0, I can do this without having any issues. And I also take the adjoint equation. So what? All right, UP P bar minus M, and I multiply on the right with gamma mu U, and that's equal to 0. So I just took the normal Dirac equation multiplied by U bar gamma mu on the left, took the adjoint equation multiplied by gamma mu U on the right. And since they're both equal to 0, I can sum them together. So 0 is equal to U bar gamma mu P minus M U plus U bar P slash minus M gamma mu U. So I just added the two equations together. And since there's 0 on the other side, then that's perfectly fine. Okay, and now we're gonna write out these explicitly. So we get equal to U bar gamma mu, and then this term, let's call it alpha, P alpha U, minus U bar gamma mu mu. And then for the second term, we get U bar gamma alpha P alpha gamma mu U minus U bar mu. Oh, sorry, gamma mu U. Okay, and now I take the two mass terms together and then take these two momentum terms together and collect the like terms. So I end up with U bar, and here the first one I get gamma mu gamma alpha plus the second one, which is gamma alpha gamma mu. Again, I can swap the order of these two with a P and the gamma without any issues. So, and then common factor P alpha U. And then the other one, these two are essentially the same. So minus 2m U bar gamma mu U. So I'm respecting the order of this U bar gamma mu U, but where this mass term goes is because mass is just a number, so I can just take it out of front and not have to worry about it. So you can see the first one here is just the anti-commutator for the gamma matrices. So if you don't remember, gamma mu with gamma nu anti-commutator is equal to 2 times eta mu nu. So this then here is equal to 2 times U bar eta mu alpha P alpha U minus 2 m U bar gamma mu U. And then I use the metric to just sum over this alpha index and then raise the mu index. So I get 2 U bar P mu U minus 2m U bar gamma mu U. Okay, so now that I got this and this is still equal to 0, so let's just concentrate on this thing. And now let's look at just the mu equals 0 component. So for mu equals 0 component of this equation, it just says 2 U bar P naught U minus 2m U bar gamma naught U is equal to 0. So then that says 2 U bar P naught U is equal to 2m U, and instead of U bar, I'm going to write it out as U dagger gamma naught. That's the definition of this adjoint spinor. And then this other gamma naught gives me U. So I took it to the other side and then expanded out the U bar. So now the gamma naught, these two, remember, gamma naught squared is equal to just the identity, so equal to 1. So I can cancel these two out. So and cancel the 2 out. So I get U bar P naught U is equal to M U dagger U. So now that tells me that, oh, sorry, one more step. So taking this u bar, u dagger u, recall that the normalization condition for the Dirac equation is that we normalize the Dirac equation by demanding u bar u to equal to 2 times the energy. So 2 times P naught. So then putting that into here, we get that u bar u must equal to 2 times the mass. Because once we sub this 2 P naught in here, the P naughts cancel out and then you end up with 2. So that's the first thing that, that's one of the first conditions that we had to derive. So this u bar u is equal to 2m. So that was that here. Okay, and the second one is quite easy now. So again, go back to this equation, but instead of looking at mu equals 0, we just look at it in general. So we say that 2 u bar p mu u is equal to 2m u bar gamma mu u. Okay, and then now that we know this u bar u is equal to 2m, then we can plug that into here. So on the left, we get 4m p mu is equal to 2m u bar gamma mu u. And then after some cancellation, we see 2p mu is equal to u bar gamma mu u. And that's the second condition that we had to derive. So these are the two conditions. Yeah, these will look very contrived, like from just looking at these derivations, because a lot of the steps, like the question asked before, like it's not obvious why we're doing it. But like physically, when you're doing an actual calculation, you never have to do this. So you can just use these conditions from this point onwards. So it's not like something that you're gonna have to memorize and know how to do in an exam. Any questions about any of this? The whole manipulating the Dirac equation? All good? Okay. If not, then let's go change the pace a little bit and do one of these ones. Okay, question 1, cross sections and decays. So calculate the branching ratio for decay kaon plus to pion plus and plus a neutral pion. Given the partial decay width of this, this process, decay width is equal to that. And then the mean kaon lifetime. So this is kaon decaying into anything. So a kaon is highly unstable. It's got a lot of different things that it could decay into. So if you just have a kaon and then wait to see how, on average, how long it decays, it's equal to this lifetime. But this includes the kaon to pion decay plus kaon to whatever else. So to calculate branching ratio is basically asking, out of this entire like overall average lifetime, how much is the kaon to pion decay actually responsible for? So like how significant is this decay out of all the other possible decays? And so branching ratio is just a number, usually called BR. It's just the decay of a particular interaction that you care about divided by the decay width of like the overall everything that the particle can possibly decay into. And using the definition that the decay width is equal to 1 over the lifetime, then we can see that we're given the lifetime. So we're given this overall decay width. So this is equal to the decay width of a particular interaction times by the overall lifetime of kaon, which is equal to just 1 over gamma of the overall kaon interaction. Okay, so now everything's pretty much the same. The only thing we have to do is that this thing is given in EV and this is given in seconds. So we're going to have to do a conversion because this branching ratio is just a ratio. So it should be a dimensionless number. So we can't have EV over seconds. So if we just put it together, then what we're going to get is 1.2 times 10 to the minus 8 squared. Yes, squared, because there's 1.2 times 10 to the minus 8 here, and then the lifetime happens to be 1.2 times 10 to the minus 8 as well. Just make numbers easier. But for units, we get 1 EV from the decay width and a second from the lifetime. So if we get out the last week's tutorial notes when they had all the natural units on there, we see that EV seconds, the constant to use to cancel that out is h bar. So h bar is going to be given in GeV seconds. So these going to cancel out perfectly. So overall, that's give us 1.2 times 10 to the minus 8 squared divided by 6.858, sorry, 582 times 10 to the minus 25. So this is EVS and bottom is GEVS. So there's another times 10 to the 9 here. But okay, if you put that in a calculator now, it will give you a nice dimensionless number, just 0.22. So if you end up getting this number larger than 1, then you probably go back and check a unit conversion, because you can't possibly be doing more than the overall decay width. So this is definitely like a less than 1 ratio. Cool. Okay, so yeah, that's it. Very simple one for calculating branching ratios. Hard part is calculating this decay width in a lifetime. So they've done all the difficult stuff for you, and putting it back together as a ratio is not the most headache. Okay, everyone happy with that? All right, maybe we actually could get everything done today. All right, let's just go on with question 2 then. That was an easy one for decay. Using expression for differential cross-section of 2 to 2 scattering in the center of mass frame in the lecture, show that the sigma dt is equal to this thing. Okay, so we're going to start off this with the t Mandelstam variable. So t is going to be p1 minus k3 squared. Sometimes there's a habit. So if you have some 2 to 2 interaction, like 1, 2, and then comes out 3, 4. Could be, okay, there's a black box in here. Could be whatever interaction it is. You label, sometimes you see that they will label the initial states with like P1, P2 for the form momentum. And then for the final states, they'll call it K3, K4. This K is not the Fourier vector K or any like other K. It's just form momentum. It's just calling a K. Sometimes I guess it distinguishes from the initial states, but it's perfectly valid if you call the final states P3 and P4. It would just be a labeling thing. Like at the end of the day, it's exactly the same. So yeah, here K, I literally just mean the form momentum of the third particle. That's the outgoing particle. Okay, so expanding this thing out. So remember P1 squared and K3 squared is just going to give me the mass. So M1 squared plus M3 squared. And then the remaining is going to give me a inner product, P1 mu, K3 mu. Okay, and explicitly writing this out, I get M1 squared plus M3 squared minus 2 E1 E3 plus 2 P1 K3 cos theta. Okay, now if you recall from the lectures, if you work from the energy momentum relations and then use the Mandelstam variable S, you can derive this relationship where the momentum P1 is given by the Callan function S M1 squared M2 squared divided by 2 square root of S. So this is from lecture. So you can derive this from the energy momentum relation, but yeah, you can just take that from lecture notes. And similarly, if you do the exact same thing, you can get for the final particle as well. K3 is equal to the Callan function, but instead of the M1, M2, because remember the Mandelstam variable S could be given as either the 2 initial particles sum or be the final particle sum, K3 plus K4 squared. So if you're using the initial particle sum to derive this, you're going to get M1 squared, M2 squared. But then for K3, you're going to be using this version where you have the final particles. So it would just be the same thing, but for M3, sorry, not M4. M3 squared, M4 squared divided by 2 root S. Okay, so these are from the lectures. You can go back and convince yourself you can get this if you want, but we're just going to take these and plug into this equation. So then we get that T is equal to M1 squared plus M3 squared and then all of this ugliness. 2 lambda half S. Let's remove this. Okay. M4 squared, and then cos theta, and then all divided by 4s. Okay, cool. So now we go back and then we take the derivative. So dt d cos theta of this expression. So here only cos theta is in the last term. So all the front three drops out. So we end up with just lambda half. Okay, I'm just going to, as a shorthand, I'm just going to write 1, 2 for the M1, M2. And then for the other one, I'm going to call it 3, 4. Because otherwise it's the same thing. Divided by 2s. Okay, so now we have this dt d cos theta expression. We're going to pull out the cross-section expression from the lecture so we don't have to derive it ourselves. So from the lecture, if you go through all the phase space integrals, you get the cross-section sigma is equal to the Callan function for 3, 4 divided by 64 pi SF 1 over the symmetry factor, and then your solid angle integral over the the amplitude. Okay, so now we have a d cos theta. You can rearrange this to be d cos theta is equal to this whole thing times dt, and we're going to sub it into this d cos theta here. So we get d sigma is equal to lambda half 3, 4 divided by 64 pi SF 1 over SF. Okay, this is good. Just be careful. This is the Mandelstam variable S, and then the center of mass factor F, and this SF is the symmetry factor. So it's S subscript F. So don't get those two confused. My handwriting might not be helping, but yeah, they're different things. M squared, and then you get 2s dt over lambda half 1, 2, and lambda half 3, 4. Okay, cool. Now we can cancel off a whole bunch of things. So the lambda 3, 4 here can cancel off with this lambda 3, 4. And then you get rid of a factor of 2 here. And then we're also going to sub in the explicit form of this f. So from the lectures, f is equal to half of lambda 1, 2. So subbing that into here as well. So subbing everything in, this d sigma turns into m squared over 16 pi lambda 1, 2. So 1 power of a half of lambda 1, 2 from this d cos theta term we had before, and another lambda half 1, 2 from this f factor. So altogether, just give you one power of lambda, and then dt over what's it, SF? Yeah, so this S canceled out with this S, and everything else checks out. So I think that was what we're meant to get. Yeah, there we go. So that's the final answer for the decay width. Not decay width, the decay amplitude. Kind of weird, this question, because you have to basically rely on like known results from the lecture notes. So it's kind of like digging through the lecture notes and finding the ones that you need. It is a big hassle doing it from the phase-space integrals every time. So I kind of sympathize with why Mikhail asked the questions this way, because in real life, you'll be looking these things up. Like you will not be deriving this like every single time. You'll just be looking in the textbook and say, I'm going to start here. Because the hard part is calculating this m squared. That's where the physics comes in. Rest of these are just kinematic factors. So there's nothing's going to change from scenario to scenario. Any questions? Okay, if not, then I'm gonna skip 3 for now because it's basically the same questions, not the same, but it basically builds off this, and the procedure is very similar. So you start off with this expression, and then you also need to do a bunch of like derive a couple of identities from the Mendelssohn variable t, and then just going into the frame where you're in the rest frame of one of the protons, and then subbing in all these, simplifying the whole thing with setting these to 0. I'll upload the solutions for all of this, so then you can see exactly how to do it if you don't want to try it yourself. But it's pretty much, algebraically, it's pretty similar to what you're doing here. So I'm not going to do it now. I'm going to go back to the Dirac equations and do the second one. Okay, let me move this a little bit. I'm going to move this all the way down the bottom so I get room. This is going to take a bit of writing. Cool. Okay. Without any explicit Dirac matrices representations, show that this thing works, and then therefore the Gordon identity. Okay, so that's 2.2. Okay. So let's just look at the first one. So starting off with the left-hand side, and then we're going to try to derive the right-hand side. So left-hand side, we have the adjoint spinor, P, and then we got this sigma mu nu, P plus K, lower index nu, U of K. Okay, so again, K and P are just both four momentum in this case. So the K is not like a Fourier vector. And it's now kind of important to recognize that this P means that this spinor is attached to, like, works with this momentum operator, and this spinor works with this momentum operator. So like you'll see later that you don't want to mix these two up. So keep the P and K labels in the equations if you can. Okay, so to start, we look up the definition for the sigma mu nu. So this is given by the commutator of gamma mu, gamma nu. So commutator is the minus version of the anti-commutator. There you go. Okay, now we put it into here. So we get I on 2, U bar P, and then gamma mu, and then gamma nu times by this P plus K lowercase nu. So we can simplify this a bit by just using a slash notation, since this is a lowercase nu, this is uppercase nu. So this second gamma matrix will contract with these two under Dirac notation. So you get P plus K slashed. And then minus, so minus now this one multiplied by the first gamma matrix, so it's going to be slashed. P slash plus K slash gamma mu. And that's it. And then U of K. Okay, cool. And then just one more intermediate step to make it a little easier to see, we're going to expand out the middle part. So we're going to get gamma mu P slash plus gamma mu K slash minus P slash gamma mu minus K slash gamma mu U of K. Okay, we want to now simplify this with the Dirac equation. So we know that we can use P slash plus M U of P is equal to 0, or in other words, P slash U of P is equal to M of U of P. Or the adjoint version, which is just going to be U bar P slash is equal to M of U bar of P. So we want to use either this one or this one. But okay, now this is why the ordering matters, because in this case, the first one here, it looks like we have a U bar P and then a P slash. So it looks like we could use this relationship to simplify to a mass, but it's kind of being cucked in the middle by this gamma mu. So I can't actually do it. It's not allowed. So this one is the only one that can. So this one, the gamma mu is on the right-hand side. So this P slash can directly go and talk to this U bar and then be simplified using the adjoint Dirac equation to simplify to a mass. And same story on the right-hand side. So this K slash wants to meet up with this U of K to be simplified to this M U. But this gamma mu is in the middle, so I can't do it to this term, but I can do it to this term. So these two can be simplified using Dirac's equation, but not these two terms. So we're going to leave these two alone and then rewrite these in terms of the mass. So we get I on 2 U bar P, and then gamma mu P slash, can't do anything about that, plus this one is going to be gamma mu and then K slash with U of K. So it's going to be M of U. So I'm just going to write M here because the U stays on the outside, of the bracket. And then minus this one. So this P slash gets to go with this and turn into an M, and then gamma mu. And then this K slash doesn't get to do anything, so it stays as it is. Okay, so now M commutes with gamma. So this is the same as this. So these two terms cancel each other out. Okay, shouldn't use a slash notation. Shouldn't cross things out when I'm using a slash notation. So yeah, you can see these two cancel out. So we end up with just I on 2 U bar P gamma mu P slash minus K slash gamma mu U of K. Okay. Now then, this is gonna take a little bit of algebra now. So let me write the thing out without the slash notation to make it a little more obvious. So gamma mu, gamma nu, P nu minus K nu, gamma nu, U of K. Okay, so the first one, I'm gonna try to simplify this by invoking the anti-commutator, gamma mu and gamma nu is equal to 2 eta mu nu. So that means gamma mu, gamma nu is equal to minus gamma nu, gamma mu plus 2 eta mu nu. So I'm going to sub out this for this. Yeah, is that what I did? Yes. Okay. So then that gives me I on 2 U bar of P. And then the first one is going to give me minus gamma nu, gamma mu, P nu, and then plus 2 gamma mu nu, P nu. And then this is going to be the same, except just flip the indices around. So same thing for the K term. So I get plus gamma mu, gamma nu. So I'm swapping the nu and mu's order around. And then K nu minus 2 K nu eta mu nu. Okay, that is correct. Just being careful. Okay, so now again, because the P commutes with this gamma, so I can take this over here, and this P nu and this gamma nu, they can be contracted into a slash. This will just take the index to the uppercase. This will contract the K with this gamma nu, and this will take the index to the uppercase. So this whole thing becomes I on 2 U bar P minus P slash gamma mu. And it's very important that you see that the P slash, because this gamma nu is on the left, the P slash is now on the left-hand side of this gamma mu. Plus P mu, 2P mu, sorry. 2P mu. And then plus gamma mu, and then K slash. The K slash is on the right-hand side of this gamma mu. And then minus 2 K mu, U of K. Okay, so why do we do all this? We went through all this just so that now we went from having the gamma mu and the P slash in this order to now the P slash and gamma mu in the reverse order. Reversing this order now puts this P slash right next to this U bar of P. So these two can now be simplified using Dirac's equation. And similarly for the second term, we now swap the order of this K slash and gamma mu. So this K slash can now communicate with this U of K, and they can then be simplified with Dirac's equation. So very similar to how we were canceling them out before. So now we get this is equal to ion 2 U bar P. And then the first one is minus M gamma mu plus 2P of mu plus gamma mu of M from this K slash, and then minus 2K of mu, U of K. Cool. And then now these two cancel each other out. So then we end up with this, take the 2 out the front. So we end up with just I times U bar P. And then we have P minus K all to the mu, since it's just these two guys left, and then U of K. And that's exactly what we're looking to do in the thing here. Okay, they took this out the front, but same thing, because yeah, those two commute. Okay, any questions? No, all good then. If not, let's just call it here today, because the second part, the Gordon's identity, now that you know this, you can just pretty much put this in here, and then the rest is the algebra is going to be really simple, because you've done the hard part of doing all this shuffling of the gamma matrices. So yeah, there's not much difference, but there's still a couple of lines to write down. And then the question 3, this one that we didn't do, you just have to remember a couple of identities. So writing them out explicitly means that you're going to have to do a lot of shuffling with the gamma matrices, but that's fine. So all you have to remember is that gamma naught is equal to 1. So what that means is that gamma naught is, in a sense, like, okay, no, that's curly brackets. It's in a sense the inverse matrix of itself. So when you multiply, you can use it as an inverse. So when you're dividing them to the other side, you can like not have to put in a denominator, because it's the same as its inverse. And then for the rest of it, you just got to remember to use the anti-commutator for gamma mu and gamma 5, and that's equal to 0. And then also remember the normal anti-commutators is equal to 2 eta mu nu. But in this case, if you have just a spatial part of one of the gamma matrices anti-commuting with gamma naught, which is what you'll be doing, you're trying to swap the order of these gamma matrices of the spatial part and the gamma naught. And eta of I is 0. There's no off-diagonal components in the Minkowski metric. So this is equal to 0. So these two relations will allow you to flip the order of gamma mu and gamma 5s while picking up a minus sign. So when you're doing this question, you're just going to be using these two relations to try shuffle them together and put the gamma naughts next to each other and then delete them, because they cancel each other out. And once you cancel each other out, then the rest of them should also then be easily canceled out algebraically. One more thing in this question worth mentioning is that the spin operator S hat, this writing in a vector form, so like Si as a component in this vector dot product, is defined as gamma naught, gamma I, and gamma 5. Okay, yeah. So if you just use this definition inside here and then go through the algebra, and you should be able to get it out. This one is not too bad in terms of the Clifford algebra. And yeah, highly recommend, if you don't already, have it like bookmark the gamma matrix Wikipedia page. That's pretty much what you have to do. Like, you don't want to memorize any of these relationships. Just scroll through the Wikipedia page, find the one you need. It's all there. So it's a really good reference to have when doing these questions. And yeah, any questions about anything? No, if not, then I will see you guys next week, and I'll post this recording afterwards. And I'll post the solutions as well. All right, thanks guys.